Welcome to episode 17 of Reggie and Royal Perspectives, Why Physical AI Must Survive Offline. Today I'm going to show you why the future of agricultural and environmental intelligence doesn't depend on cloud connectivity, it depends on intelligent design that works anywhere, anytime. Before we take a specific dive into a specific internet platform, known as LeafEngines, based upon the rapidly rising MCP protocol, we'll explore the broader landscape of why the future of autonomous machines, food security, and national defense depends on intelligence that can thrive in the dirt, without the cloud. According to recent Medium and PR.com press releases and articles, LeafEngines is a patent-pending, hardware-agnostic agricultural intelligence and environmental MCP, Model Context Protocol, platform. It integrates multimodal signals, from satellite imagery to local soil probes, with agency data from the USDA, EPA, NOAA, and NASA to provide actionable, edge-deployable farm and conservation data. Emoji, key capabilities. LeafEngines translates complex environmental and agricultural data into readable, auditable insights, soil and water intelligence, instant analysis of soil composition, pH, texture, suitability, and local water quality. Crop recommendations, AI-generated planting windows, suitability rankings, and yield predictions. Sustainability insights, built-in carbon credit calculations and environmental impact assessments. Offline-first architecture, designed to provide deep canopy and remote location offline support with local plant identification and GPS-independent field positioning. Section 1. The illusion of the cloud and the reality of the dirt. The paradigm shift. When we picture the absolute pinnacle of modern technology, most of us imagine pristine, perfectly climate-controlled server rooms. Endless rows of black racks, blinking blue lights, environments that are completely sterile and entirely predictable. Temperature, humidity, redundant power supplies, every conceivable variable is managed. The data center is, by design, the definition of engineering perfection. It exists specifically to coddle fragile systems. And for the last 15 years, AWS, Azure, and the promise of high-speed internet reinforced a seductive narrative, that the cloud was essentially infallible. Like gravity, you just assumed it would always be there. That assumption has lulled an entire generation of engineers and operators into a false sense of security around the concept of ubiquitous connectivity. The physical divide. But then take that brilliant, perfect technology and try to drop it into a 10-ton piece of heavy machinery operating in the middle of a muddy field during a severe storm. Suddenly, that pristine logic just chatters. The technological landscape of the physical world is completely and utterly chaotic. The cloud is fantastic for parsing massive data sets or rendering complex video files. The physical world, however, does not care about clean data structures or perfect API calls. Consider the vivid contrasts our sources describe: a massive dust storm sweeping through a California orchard, not just low visibility, but static charge and dirt aggressively coating antennas, completely degrading signal integrity. A combat zone where communication signals are intentionally jammed by an adversary. A routine hurricane tearing through a coastal region and physically severing a vital fiber optic cable. In those moments, AWS doesn't matter. Azure doesn't matter. If the cable is cut or the signal is jammed, the machine is completely isolated. The cost of latency. The source material gets very specific about the immediate cost of that isolation, focusing on the physics of latency. We are not talking about minutes of downtime. We are talking about the catastrophic cost of a mere 2-second delay. As consumers, we are conditioned to ignore it. A network drops packets on a smartphone and we get a buffering wheel, mildly annoying, maybe a sigh while waiting for a Netflix video to load. But inject that exact same 2-second latency spike into a 10-ton autonomous harvester moving at 15 miles per hour. It is not a buffer. Momentum does not pause just because the Wi-Fi dropped. 2 seconds at that speed means a machine travels over 40 feet in entirely unguided motion. That is a collision. A collapse. Or worse, a fatality. Greater than latency is the silent killer in physical AI. When an autonomous machine relies on a server 1,000 miles away to make a decision, any degradation in connectivity doesn't just slow performance, it creates a window of blind, unguided physical force. Reggie and Royal Perspectives, episode transcript. The question this raises is fundamental: what happens to the logic of the physical machine the exact millisecond it loses its tether to the cloud? It does not freeze safely in place. In the physical world, energy carries on. Hydraulics continue to pump. Gravity continues to work. which means the intelligence operating that machine has to fundamentally change, or the machine has to survive without any intelligence at all. Section 2. Garbage in, deadly out, the crisis of physical AI. The agentic leap. There is a critical distinction happening right now in AI development, the shift from generative AI to agentic AI. Agentic AI is not an intelligence that merely generates a poem or summarizes an email. It is an AI that is authorized to take physical action, steering wheels, accelerating engines, deploying payloads. Giving an AI model a steering wheel introduces a completely new paradigm of risk. We are placing powerful modern models in charge of heavy machinery. And if those models require a continuous connection to the cloud to verify their reality, they become dangerously brittle. The sensor problem, multipath errors. The source material introduces a critical vulnerability called multipath errors, and understanding the mechanics shatters any comfortable assumptions about GPS-based navigation. We generally treat GPS coordinates as absolute truth. But a GPS signal is simply a highly precise radio wave beaming down from a satellite. To calculate an accurate position, the receiver on the machine needs to measure the exact time it takes for that wave to arrive. In open conditions, this works well. But in complex physical environments, a deep canyon, a dense forest canopy, an orchard, or even next to large metal shipping containers, that signal doesn't travel in a clean straight line. It bounces. Off trees. Off canyon walls. Off metal siding. The physical bounce delays the radio wave by a tiny fraction of a microsecond. In the mathematics of GPS, a microsecond delay translates to a massive spatial error. Because the signal took longer to arrive, the math tells the receiver it is farther from the satellite than it actually is. The AI suddenly thinks the machine is 30 feet to the left of its actual physical location. The hallucination danger. Now consider what happens when an agentic AI acts on that corrupted signal without local context to catch the error. If a large language model hallucinates in a chat window, it's a funny typo. We screenshot it and post it online. But if an AI agent hallucinates based on a bounced GPS coordinate, it forcefully drives a tractor directly into an irrigation ditch, or confidently drops a payload in the entirely wrong grid quadrant. Episode transcript. This exposes the core limitation of the omniscient AI narrative. These systems are strictly, entirely, only as good as the telemetry data they are fed in that exact millisecond. Nothing more. If the internet goes down or the GPS signal bounces, the AI becomes deaf, blind, and highly dangerous, unless it possesses localized context to recognize that the data it is receiving is mathematically impossible. Key takeaway: AI is only as good as the data it acts on. If the internet is down, if the GPS is bouncing, the AI is blind, deaf, and dangerous, unless it has local processing power to verify its own perception of reality. Section 3. Food security is national security, the dual-use reality. The vulnerability of supply chains. Think about a weekly grocery run. The produce aisle. Modern farming is not a solitary farmer making gut decisions about the weather. It is an industrial operation utterly dependent on precision agriculture and synchronized satellite networks, and the scale of that dependency is staggering. Massive fleets of tractors, autonomous harvesters, complex irrigation grids, all orchestrated via delicate digital threads communicating with centralized cloud servers. The global food supply chain is running on a knife edge of connectivity. So if a targeted cyber attack takes out a regional network, or a severe solar flare disrupts satellite communications, global food production does not experience a minor slowdown. It stops. It experiences a hard halt, because the centralized orchestration layer is gone and the machine simply will not know how to operate collectively. Food security is national security. The defense parallel. The source material draws a direct technological parallel that completely reframes the stakes. Think about a commercial tractor trying to navigate a dense orchard where GPS is bouncing off trees. That tractor is facing the exact same mathematical and technological problem as a defense drone operating in a combat zone where an adversary is actively jamming the signal. From an engineering standpoint, the commercial orchard and the active battlefield are the same environment. Both are classified as denied environments, where the machine has been forcibly cut off from the cloud, is entirely on its own, and must navigate, make decisions, and take physical action without any external processing power coming to its rescue. It seems wild that a piece of agricultural equipment and a military drone share the exact same central nervous system vulnerability. But they do. And that means the solution is the same across both industries. Geopolitical stakes. Whichever nation, or whichever organization, figures out how to make offline, edge-capable AI work reliably will essentially control the future of physical infrastructure. This is not about selling better farm equipment or better drones. This is a matter of geopolitical sovereignty. The engineering mandate is clear: we have to teach the machine how to survive on its own, in the dirt. The focus has to shift from relying on the cloud to empowering the machine itself. Nations that control offline, edge-capable AI will control the future of physical infrastructure. It is a matter of sovereignty. Royal. Section 4. The algorithmic immune system, uncertainty gating. The concept of doubt. The stakes are global. The cloud is vulnerable. The physical world is chaotic. But the source material outlines a technological solution, and it centers around a fascinating concept developed by a platform called LeafEngines. They call it an algorithmic immune system. The idea is profound, teaching a machine to actively doubt its own sensors. Historically, a sensor feeds data to a computer and the computer simply obeys it. The sensor says X, the computer does Y, no questions asked. The LeafEngines approach introduces a mechanism called uncertainty gating, which changes that architecture entirely. Kalman filters, explained simply. To understand how uncertainty gating works, we need to look at a piece of underlying mathematics, the Kalman filter. But forget the equations. Think of a Kalman filter as a continuous engine of predictive state estimation. It doesn't just take a sensor reading at face value. Instead, it maintains a continuous mathematical model of the machine's physical state, its velocity, its mass, its current heading. It knows what the machine is currently doing. When a new sensor reading comes in, the filter calculates the probability of that reading being true, given what it already knows about the laws of physics and the machine's previous state. It constantly weighs incoming data against historical momentum. The document offers a crystal-clear example of this logic in action. Greater than my GPS receiver is screaming that I just moved 50 feet to the right in a single second. But my wheel rotation sensors are telling me I have not moved a single inch. And my internal accelerometers did not register any lateral g-forces. That GPS reading violates the physical constraints of my model. It is mathematically improbable. Confidence score, 0. Filtering it out. Reggie, illustrating Kalman filter logic. The filter identifies the anomaly, the infection, if you will, and isolates it. The larger agentic AI does not act on a hallucination. We are, in effect, programming a gut feeling into the machine. We are teaching it skepticism as a survival trait. The offline requirement. Here is the absolute necessity, the crux of the entire argument: this immune system must live locally. It has to live at the edge, physically on the hardware, completely offline. If that skepticism requires a round-trip ticket to a server in Virginia to ask my wheel sensors and my GPS disagree, what should I do? Then it's game over. The latency of that query negates the safety entirely. If the machine has to ask the cloud for permission to doubt a faulty sensor, the physical mistake has already been made. The tractor is already in the ditch. The result: graceful degradation. By placing uncertainty gating directly on the edge device, you allow the machine to degrade gracefully. Rather than a single bad GPS signal causing an entire 10-ton machine to veer wildly off course or trigger an emergency hard stop that damages the equipment, the machine simply recognizes the bad data and ignores it. It relies on its remaining trusted sensors, cameras, LiDAR, wheel encoders, and either continues its mission at a slower, safer pace or brings itself to a controlled halt. Core principle: graceful degradation over catastrophic failure. A machine that can doubt its own senses and continue operating on trusted data is infinitely more resilient than one that either blindly trusts corrupt input or halts entirely when a single sensor fails. Section 5. The Open Source Rebellion and Model Context Protocol. David versus Goliath. There is a massive contradiction staring us in the face once you understand all of this. We have just described algorithmic immune systems, continuous mathematical modeling with Kalman filters, agentic AI taking physical action. All of this sounds like it requires massive GPU clusters and billion-dollar data centers. If you cut the cord to the cloud, are you not starving the AI of the processing power it needs to actually think? This hardware limitation is exactly what is being solved right now. The current AI landscape is largely monopolized by massive tech giants hoarding compute power. But that is changing, quickly. The intelligence is being decoupled from massive compute clusters through a breakthrough in how AI communicates with local hardware. Model Context Protocol, MCP. The source material points to a specific framework called the Model Context Protocol, MCP. To understand its significance, consider how traditional AI agents access hardware. They reach out through an API over a network stack, they ping a server, format a request, authenticate it, and wait for a response. That networking overhead consumes an enormous amount of processing power and introduces latency, even if the server is relatively close. MCP fundamentally changes that architecture. It is a standardized protocol that allows localized AI agents to securely access local tools, local sensors, and local files without ever invoking a network stack. It builds a secure, closed loop right there on the motherboard. By stripping away all the bloat of networking protocols and cloud authentication, MCP creates a hyper-efficient localized environment where the AI model can query wheel sensors, check a column and filters confidence scores, and adjust a steering column in a fraction of a millisecond. Because the compute overhead is so drastically reduced, you can run powerful quantized AI models on standard ruggedized laptops or field devices. You do not need a billion-dollar data center to have highly intelligent, resilient systems. The Edge Rebellion, empowering the builder. This represents what the document calls the Edge Rebellion, a complete shift in the power dynamic. Innovation is no longer trapped inside Silicon Valley server farms. It can happen in agricultural hubs, mining towns, defense startups, and garages. Everyday builders can now create enterprise-grade, offline-first systems without asking permission from the tech giants who have long hoarded all the compute power. You now have the power to build enterprise-grade, offline-first systems from your garage. The democratization of this technology is real and it is immediate. Reggie, Episode Transcript. Section 6. The Sandbox Challenge and the Future of Autonomous Infrastructure. The Developer Challenge. This is not theoretical research locked behind an enterprise paywall. The core foundation of this offline revolution, the LeafEngines base server, is open source. It is sitting right now on GitHub, available to anyone. The challenge to developers is direct and tangible: download the server onto your local machine, physically turn off your Wi-Fi router, and see if you can build an agent that successfully reads local hardware and makes a decision. They are putting their money where their mouth is. According to a recent Medium and PR.com press releases and articles, LeafEngines is a patent-pending, hardware-agnostic agricultural intelligence and environmental MCP, Model Context Protocol, platform. It integrates multimodal signals, from satellite imagery to local soil probes, with agency data from the USDA, EPA, NOAA, and NASA to provide actionable, edge-deployable farm and conservation data. Emoji. Key capabilities: LeafEngines translates complex environmental and agricultural data into readable, auditable insights: soil and water intelligence, instant analysis of soil composition, pH, texture, suitability, and local water quality. Crop recommendations, AI-generated planting windows, suitability rankings, and yield predictions. Sustainability insights, built-in carbon credit calculations and environmental impact assessments. Offline-first architecture, designed to provide deep canopy and remote location offline support with local plant identification and GPS-independent field positioning. The Enterprise Wedge, 5-slot pilot program. For larger, established operators, those in agriculture, defense, and mining who are feeling the operational pain of connectivity loss right now, LeafEngines is actively seeking partners through an exclusive 5-slot pilot program. Only 5 slots. LeafEngines is looking for organizations who need to deploy this offline algorithmic immune system into the field immediately. The goal is to move from the sandbox to the dirt. The final perspective. The closing philosophical thought from the original document reframes the entire trajectory of the tech industry. True technological advancement is not about making things more complex, more bloated, and more dependent on fragile cloud infrastructure. Real advancement is about making systems resilient in the dirt. Elegance in engineering is not about thriving in perfect, climate-controlled conditions. It is about maintaining functionality when every environmental condition is actively working against you. Here's a pertinent quote: "The cloud is great for data. But the future of physical intelligence is being built in the dirt." The next frontier: swarm intelligence and collective offline negotiation. There is one more concept worth sitting with. We are now taking massive multi-ton physical machines, cutting their umbilical cord to the cloud, and teaching them to form their own localized truth about the physical world based entirely on internal mathematical models and localized sensors. Each machine exists in a completely isolated perception of reality. Now imagine a scenario where a signal-jammed orchard or an active battlefield is not dealing with one isolated machine, but a swarm of multiple offline autonomous tractors or drones. Each individual machine's Kalman filter is crunching its own localized sensor data, and therefore each machine is determining a slightly different truth about where it is and what the physical environment looks like. If machine A's localized model determines the path is clear, and machine B's localized model determines there is an obstacle, and they have absolutely zero connection to a centralized cloud server, how do they reconcile that? How will these machines negotiate and cooperate with each other, completely offline, without a central cloud referee to tell them whose mathematical model is actually correct? That is the next great frontier of physical AI, moving from individual offline resilience to collective offline negotiation. From teaching one machine to survive in the dirt, to teaching a swarm to find consensus in the mud. Sign off. Are you ready to join the developers who are already building offline-first environmental intelligence applications? Start your journey at docs.leafengines.com, easy to remember, comprehensive in content. Whether you prefer the user-friendly docs.leafengines.com interface or want to dive deep into the technical GitHub repository at github.com/corendo/soil-sidekick-pro-guide/tree/main/docs/partnerships/, you'll find the same powerful documentation. You should pause the audio and place that path in a search engine. Essential reading for your next steps. Start with the white paper, Data Integrity at the Edge, complete technical architecture that powers today's real-world activity. Explore the 10 use cases, LeafEngines_MCP_10_use_cases.md, see exactly how developers are creating revenue-generating applications offline. Dive into deep dive guides when you're ready to implement Node-RED integration, Cloud MCP integration, enterprise onboarding. Get your free sandbox API key at app.soil-sidekick-pro.com/API docs and start building with the same endpoints that process today's 11 real-world calls. Remember what we learned today: every failure was a developer discovering business value. Every endpoint call was proof that physical AI survives offline. Every use case represents real revenue opportunities in agricultural intelligence. The same journey that took developers from free soil data to premium agricultural intelligence today is waiting for you at docs.leafengines.com. Thank you for joining me on Why Physical AI Must Survive Offline. Stay innovative, stay offline, stay intelligent. For our 30,000+ listeners across 50+ countries, whether you're listening in English, Chinese, or Korean, the documentation is ready at docs.leafengines.com. Start building your offline-first future today. Check the show notes for links to the original white paper entitled LeafEngines_white_paper_data_integrity_at_the_edge.pdf, which will be located at docs.leafengines.com, with access to the Sandbox Challenge located at LeafEngines_agricultural_intelligence on the GitHub site, and all the details on applying for the 5-slot pilot program. For operators ready to move from theory to field deployment, search for the LeafEngines MPC server, or LeafEngines on Node-RED, or LeafEngines on N8N, or LeafEngines on ClawHub. On our next podcast in episode 18, we will conclude with the second installment from episode 15 entitled Billions of Brains, the Global AGI Invasion in Your Pocket, where we embarked on an exciting journey of understanding and preparing for the AI landscape, which is undergoing its own seismic shift. A wave of new language models flooded the market, each promising to push AGI closer to reality. So be sure to catch us next time, for Reggie and Royal Perspectives podcast on the economy, cryptocurrency, history, and business. If you enjoyed the podcast, don't forget to smash the like button, and subscribe to our channel. Until next time, let's get busy.